Sorry for repeating history, but here we are at Holden again. My favorite place. I know this has not been very exciting nature-wise. I do promise on the weekends and other places I will go, other times I will go to other places around here. Don't think we've even been to Jordan Creek Park yet. I don't know if this is as much a nature channel as it is, I guess, a musing channel, or a philosophical, if you want to call it that, or just my journal for what it's worth, which probably is not interesting to most people. But like I said, I'm not trying to make this interesting. This is not an entertainment thing. I guess this really always was about me having a lot of things on my mind that I wanted to say, and this is a forum for me to do it. When I'm walking is usually when I'm doing my most thinking. The moon's up there. You probably can't see it in the video. It's very cool to see the moon on a very blue sky. I always love that image. This is what I do anyways, and so I just thought of recording it. Like, why not? The space on YouTube is free, apparently, at least for now, and I can record these videos of me for whatever purpose, or even for no purpose at all. And it is what it is, I guess. I don't know what this is, but it is what it is. That's kind of my philosophy of life, and things are what they are. See things as they are. This is what it is. Not emulating anyone. It's interesting, someone made a comment, I think, on one of my videos. I don't remember the exact nature of it, but the implication being, is this a ripoff or a copy of some other channel that I've never heard of before? And I didn't bother to look that channel up either, because I'm like, I don't know, maybe not. It certainly isn't the intention, and I have no knowledge of these other channels. I'm doing what I'm doing. What other people do is up to them, and there's enough channels out there where people go to this place and to that place and make it entertaining with music and all that. That's not what this is about. So what it really is about, like I said, is just me getting out and walking every day, and that's what it's always been about. And decompressing, I guess, in some sense. This maybe initially always started off as some sort of decompression, of my mind, with all the hectic activity of my life and my job. That me just coming out into nature always brought me back to a very simple realization of what life is all about at its core. And we should never forget that. We should never lose our relationship with nature. If you lose your relationship with nature, you lose your relationship with humanity. And so, yeah, there's a lot of activity here today, it looks like. I don't know what's going on. A lot of vehicles and people, volunteers and workers. I guess I'll take it, maybe I'll walk this way. I tend to avoid areas where I think there's going to be a lot of people, because I think people don't want to be recorded, for one. And also, I just prefer the quieter places for when I'm contemplating or doing whatever, inquiring. This is the tree alley. I'm not pronouncing that correctly. Which I think essentially is alley. Tree alley in French. Well, this is a very nice walkway. I always like it. If you just you can get used to something if you see it. It's familiar. And I always try not to get used to things. Well, I actually don't try not to. I just don't get used to things. Every day I see as being new and fresh, regardless of what was there yesterday. And that is definitely true here. And it's also a reason why I don't mind coming here every single day, because it is always different. And that's what you have to see, right? Like, just that when you're paying attention, every day is unique. It's absolutely unique. If you're not paying attention, it may seem the same. And that's because you're thinking in abstract terms. Oh, it's a walkway, it's trees, it's flowers. If that's all you see, then you're not really seeing. And you say, okay, trees again, flowers again, walkway again. It's like, are you really looking? Are you looking closely at the flowers? Seeing how they change every single day, seeing how they move in the wind, you know, seeing how everything changes. I mean, if you see that, then every day is fresh and new, and you're not seeking newness, right? Or entertainment. So, I mean, that's also I think the essence of this channel, if you want to talk about it in some sense, is just reminding people of the newness of every moment. And that if you pay attention, that's where you find truth, right? Not in a book, not in anything someone tells you or teaches you, but just being aware of what's around you all the time. There's nothing more than that. That is it, to be completely aware of everything, through all your senses, you know? The opposite of, I think, what people do. I'll continue down this way just a little bit. You know, and like trying to remove yourself from the world. Don't remove yourself from the world. Become immersed in it. But not in the superficialities, but in the depth of everything. Right? The depth of everything that is found by being aware of your senses. What you're seeing and hearing and smelling and tasting, and even in the combination of all those things, not any one thing, not just what you're smelling or seeing. You know, as I walk through here, and again, the description is not the thing, but I can smell like the flowers, and I love the smells as they change almost every day. I mean, I've been noticing the smells are different since spring arrived, just as I do every year. And every day it's different. And then the sights, I mean, the ferns and the various plants. Sometimes I stop and see what they are, but most of the time it doesn't matter to me what they are, because they are what they are. Don't need to know the name. And this is another problem. We have this habit of naming things and wanting to know the name and to learn about that thing through knowledge. Chipmunk friend. Why do we do that? Like, why do we have to know about something in the conventional sense when we can know it directly? You know, experience it, like go into it, like there's a universe inside everything if you listen. You know, you don't need to describe in limited words what something is. How does that description help you at all to understand what something is? Like, that you can see and observe directly. Like, that's the beauty of living, is not explanations. No one can explain life and what it is. It's like you have to live to know what life is. There's no other way. And this simple truth is something people forget when they get caught up in the world of ideas that we've created, and they live in that world. And this is why sometimes I wonder, why are there not more people here? You have a wonderful place like this. I know why. Because this is out here in the real world, right? This is the truth. And most people are still living in their digital cage that they've created for themselves. Some people may say, well, no, society's created it. But you're part of society. You're driving it, right? What you do is society. So don't forget that. And think, that you're separate from society. And in that society, you feel comfortable inside your digital cage or digital prison, whatever it is. Right? And I suppose I'm still slightly inside that digital prison because I haven't completely unplugged here. I'm recording all this, right, with technology. But I'm doing it with the sense of just saying, get out. Like, just get outside and, just see what's around you. I mean, you can do this in a city too, but, a city is the creation of the human mind, right? The entire city, from the buildings to when you think about it, right? You are living in a city, you are living inside of a conceptual contraption of the mind. That city itself was envisioned by a mind, not one mind, right? The human mind over millennia. I mean, when you think of the oldest cities, the ruins of these oldest cities in Mesopotamia, or wherever, I think Iran or Iraq, or where the earliest remnants of cities are. And when you think of, how far we've come, but then how far we've not come, how we're still the same, in many ways, still as barbaric, why we haven't learned to live together in peace yet, after all this time. Back then it was tribalism, and now it's nationalism. It's just tribalism on a grander scale. And this doesn't make a whole lot of sense to me. But this makes sense to me. Being out here makes sense. And not in any logical way, in any rational way. Although it is rational and sane. In fact, this is the most rational and sane thing there is. To be in nature, unspoiled nature. You could say this is slightly spoiled. It's not completely wild here, and it's manicured in a sense. Humans played a part in putting this place together, there's no doubt. I mean, everything, that pond is actually a completely man-made pond, and the trail around it, of course, is, and the benches, and even the layout of the plants. But beyond that, right, like, humans didn't make the trees, they didn't make the plants, they may have arranged them, right, but it's not a remaking, it's not an invention, it's creation, it's different. Creation and invention are different. Invention comes from the human mind. Creation is what's happening all the time. It's not creation once and then. It's like everything is being created and destroyed, like, simultaneously all the time. It's just the nature of life, what it's doing, what the universe is doing is creation. You can call it that, call it meditating, what the universe is meditating, however you want to see it. It's existing, and non-existing at the same time. So I did think there was something that I did think of talking about today from the realm of knowledge, because it's been on my mind, and I've talked about it before. This is going to be a theme, I suspect, that's going to come up, because beyond contemplating life and existence, and even not contemplating it, just being out here and being present and seeing what is, which is the most important thing, there are, other aspects of life come in, and one aspect we've talked about is trying to understand maybe causal relationships, if you want to think of it that way, the world of cause and effect, this physical world that we are all in, no doubt. We see order. I mean, the natural world around us behaves a certain order, and even the human societies that we've created have a certain form of order. But we try to understand things, and we can partially understand certain things. But I do always appreciate when it feels like our understanding is getting a little deeper, a little more broad, a little more holistic. And this whole idea of information, and there's something called information theory, and I brought up in a previous talk, maybe more than one, something called infodynamics, which is sort of a current work. I mentioned a paper published last year where somebody was sort of showing that the laws of gravitation can be explained, I guess if you want to look at it that way, in terms of information, in terms of this simple law that somebody has postulated, right? And this is the thing, right? It's not truth, and it's what you see and observe. It's a postulate that says that the informational entropy, which has a measurable definition in this world. So this is within the world of measure, not the immeasurable, right? But within the world of measure. It seems that information tends to, there's two ways of looking at it. Informational entropy, which is sort of, here, let me state something, and then I'll explain. The universe doesn't like surprises. The universe doesn't like surprises. And then there's actually a precise definition of what surprise is. And it's interesting that the evolution of the universe appears to be such that there are fewer surprises. And there's a lot to say about this. This comes from information theory. So something I've been doing some reading on, because I do want to know more about this law of infodynamics. It's intriguing to me because I studied physics my whole life. And to hear that there can be sort of a law or something that can explain not only physics but also biology, also is used in transmission of data across the airwaves. So like what's happening right now with this camera and with me speaking and this video, like we take for granted, but a lot of technology has gone into creating these things, which are pretty amazing. And it turns out that there is a common thread throughout all of these things. Nature, even the genetic code, DNA itself. There is sort of a way of looking at all of this in terms of information or surprise, which I'll also mention, or informational entropy. And it forms the backbone of a lot of these technologies. And I don't think a lot of people are aware of this. You know, we think of mass and energy as being maybe the most fundamental aspects of reality, and it may turn out that information is the more fundamental nature of reality. A very different way of looking at the world, but it turns out it's sort of becoming true, or becoming more true, as we learn more about information theory and how it links to other fields of science and understanding. And this is why I'm interested in it, because I went into physics initially saying, well, I wanted to understand all the disparate phenomena in the world. And this is actually interesting too, because I think there's a connection with information. And why do we want to understand things? Like this desire to understand is also related to information. But I went into physics because I was hoping to get an understanding of a simplified understanding. And I think that's the key, simplified understanding of nature, reality, what was around me. And physics explained a lot, right? It said that a lot of things that you observe in the world, there are explanations for, there are mathematical formulas for, that can be used to predict. And I think that's the key term too. And that actually has a lot to do with this concept of surprise that I will discuss. Predicting and the inability to predict. And in fact, another statement of the infodynamics would be that the universe tends to want to always improve how its prediction of things. It acts in a way that there's less uncertainty, less unpredictability, less surprise in the world. and more order. And order, another way of looking at order and disorder, I think we talked about this before, this is all related. Order is when there's a pattern. Order is when you can explain something, when you can predict something. Another way of looking at order and disorder, I think, is predictability. A disorderly mind is very hard to predict, right? Erratic behavior, what we call irrational behavior. Or if we say someone's insane, what we're saying is their behavior is somewhat unpredictable, right? Like they may think they're Napoleon Bonaparte. They may just pull out a knife and stab you at any moment in time, right? And reason why. I just saw a very unsettling news article this morning about a man, I think it was in Maine, that tried to drown like a 60, 70-year-old man, like trying to drown like a 21-year-old boy, because they were jet skiing in some some pond that was only supposed to be used by residents, and then the guy like attempted to kill this person, and it's like, this is insane to me, right? It's insane. That's disorder. Like, it doesn't make sense, right? Things that don't make sense are disorderly. Things that make sense, there's an explanation for it, we understand it, it fits within our frame of reasoning. That's what we consider orderly, right? Like, you can consider an orderly mind as one that has few surprises. You know, it's somewhat predictable. Perhaps, maybe I'm going down the wrong path here, but there's a predictability to it, a peaceful mind, you know, not one subject to violence or to irrational behavior. There's a calmness. I don't know. There's a beauty in like this, a sense of sameness in some sense, which, you know, so let's talk about this a little more mathematically, and not to go crazy, but this is interesting stuff. A lot of this I knew in various ways, but what's interesting is information reframes probability in a different way. And it's interesting how just a slightly different way of looking at the same thing can lead to new ideas. So I'm very familiar with the concept of probability. It's something I use at work. I've studied it. I've built software around it. I use it to predict things, you know, in industry, a lot. I've written papers about it. What I really knew very little of is information. And it's strange that I didn't know that much about it. And I just picked up my first book on information theory. I don't remember the author at the moment, but it was a very simple book that I just bought on my Kindle, and I've been working my way through it. And this could have applications with work, but this is more, at this point, getting to this understanding the universe question. You can ask, why should we try to understand the universe? And that goes back to everything that I've said before. We don't need to, and shouldn't at the most fundamental level. But we still, as human beings, we have a desire or a need for more order in this universe, right? And that is what's interesting, because that fits right in with this theory of information, this second law of infodynamics, which states that the universe tends to, I think the formal statement, and it requires some explanation, is that the informational entropy of a system tends to increase over time and reach a constant in equilibrium. But the important point there is the informational entropy, which you can think of as informational disorder, or sorry, I think I stated it exactly wrong. That decreases over time, not increases. The entropy, the disorder, the unpredictability of the system decreases over time, which means the opposite of that, which is, you could regard as predictability, really predictability, the ability to not be surprised, right, increases over time. That's almost like learning, right? If you think about, and this is fascinating, and I know I'm not even defining things yet, but so let me define. There is actually a mathematical definition of surprise. And in information theory, it's usually on the first few pages of the book, which it was in this case. And you can define the surprise of any event, a probabilistic event, say tossing a coin, or something that has an uncertain outcome. You don't know until after the fact what's going to happen, but you can predict it with some probability. So there you go. That's basic probability. Surprise is the negative log base 2 of that probability, that event probability. You think, oh, it's just a mathematical manipulation of that probability, but it has a lot of significance, that particular expression. And this is what belies the importance of this, because one may say, oh, it's just probability. It's a reframing of probability in terms of information. And that is insightful. So in that definition that the negative log base 2, and there's a reason it's log base 2, because it's related to bits of information, zeros and ones. We think of bit, binary digit, right? It's a bit. And in computers right now, we use zeros and ones to represent binary states. And all of computers relies on these bits. Everything's processed at that level. Information, right, is being processed at the bit level, which you can think of as the smallest unit of information, the bit. Because essentially, it's the answer to a yes or no question. Is it this? Yes, no. And yes is often represented by 1, no often by 0. And so you can think of binary as just the answer to a question that requires that bit of information as the answer, right? And then the more bits you have, the more questions you can ask, the more information you now have. And you can think of every answer to that question as being information that is then stored in the binary digits of a computer or even of your mind, right? If you ask someone a question, are you, well, I was going to say, are you male or female? But that could be a loaded question. Like, I don't know. Are you, just about, unfortunately, not many questions have sometimes just simple yes, no answers. And you can also get to that more complex questions by asking more binary questions, right? So it's not a problem. I guess a simple question would be, do you live in Ohio or do you not live in Ohio for the time being, right? And that has a fairly definite answer of yes or no for most individuals. I mean, you can have people that live in multiple states. There's exceptions, but whatever. Let's keep it simple. Or think of this in terms of the game of 20 questions, which actually is kind of interesting, right? Is it bigger than a bread box? Is it smaller than a bread box? Is it animal or vegetable? Is it soft or hard, right? That's actually a really good way of looking at this information, because we know, and it actually explains how that game works in some sense, right? You can ask within 20 questions, it turns out, if you asked appropriate questions where each time you were essentially halving the number of outcomes, you can, I think it's over 1 million possibilities can be represented by 20 questions, because essentially it's 2 to the 20, whatever that number turns out to be, which I believe is a little over 1 million possibilities can be represented by the answers, the yes or no answers to those questions. So if you think of it as a word, somebody thinks of a word and says, I want you to guess the word, and you ask questions, you know, is it bigger than a bread box? Or no, is it animal or vegetable? And you're often trying to come up with questions, right, that narrow the field by 2 every time, right? Like if you ask a question like, is the word in a dictionary? It's not a very useful question, which also gets to that is a very important point, because that question contains little information. The answer to that question, is the word in the dictionary, is not a good question, precisely because it doesn't contain much information. You don't learn much by the answer of that question, because the answer is almost always yes. Or you could say, does the sun rise in the east? It's a question, but it contains little information. And this is very important. Why does it contain little information? Because we already know the answer. If you already know the answer, which means the probability is almost 1 of that being true, you're not surprised by the answer if somebody comes back and says, yes, the word is in a dictionary, or yes, the sun rises in the east. Okay, that's what I thought. But it's what you thought before. So you haven't gained much knowledge by asking that question. So that's not a very valuable question, in the sense that that question does not contain useful information. The answer to that question does not contain. You know just about as much after someone answers that question as you did before. And therefore, you didn't learn much, right? Learning is like when you gain knowledge that you didn't already have, in that sense. One way of learning. And this is all leading to, information, right? This is all about information. This is why this is so interesting, right? Because you can just talk about normal situations in life, such as, playing the game of 20 questions, and it's related to information. But most people don't know what information is or how to quantify it. And this is what Shannon did, right? All this work was sort of seminally done, I think it was in 1949, by this fellow Shannon. Don't know a whole lot about him, but I know it's called Shannon's informational entropy, which is what this is related to, which is related to this surprise that I just mentioned. And it is a measure of information, a quantifiable measure of information that you can evaluate any question as, is that question useful or not, by its informational content. And here's how you do it, right? So you have the probability of an event before you ask the question, and then you ask a question, and then you get an answer to that question, and you assume there's no error in that answer, at least at the moment. You now know which outcome it was. So let's say tossing a coin. Before you toss that coin, you don't know, there's equal likelihood of it being heads or tails. You don't know which it is. After it's tossed, there's an outcome, heads or tails. And if you observe, you'll see, okay, it was heads, it was tails. That's useful information, because now you know the outcome of that result. And it turns out that a situation like that, where the probability of each event is 50-50, when it's a simple, yes-no question, basically, that has the highest informational entropy, which means that question also the answer to that question contains the most information you can get, because both outcomes are equally likely. So when you determine one, you determine the outcome to be one or the other, you eliminate the other one, and you gain a lot of information from that. So the probability is 0.5, right, of having heads or tails. And so if you if you actually take earlier I defined this is a little difficult to do math here, because what you need to do is, in a situation like that, where the probability of the event is, say, 0.5, you have to sum over all possibilities, and then the informational entropy of each possibility, and that leads to the mathematical expression. You basically have to take it's the expected value of the surprise of each event that can occur, which is heads or tails in the case of a coin. Each probability is 1/2, and the expected value is found by multiplying each of those values by the probability. So it's the negative probability times the log base 2 of that probability summed over all possible states, which in this case are just two, heads and tails, and gives you the answer, right? So so the answer actually in each term, very simple expression here, I know we're doing math in the head, each of those, the log base 2 of 1/2 is equal to the negative log base 2 of 2, which is 1, right? But there's a negative in front, so the negatives cancel and you just get 1. But then you multiply by the probability of the event, which is 1/2. And so it's the same for heads and tails. 1/2 plus 1/2 equals 1. So the informational entropy of a coin toss, a fair coin toss, where the probabilities are the same, is 1. And what's interesting, that means you need 1 bit of information to store the outcome of that result. And we already said this before. In other words, a coin toss being heads or tails, if it's heads, say that's the number 1, and if it's tails, that's the number 0. And that 1 bit of information, 0 or 1, can encode the result of a coin toss. That's what the informational entropy tells you, is how many bits are required to store the result of that event, given that you don't know it, that it's equally likely, and that in this case it's not always equally likely. That's also handled by the expression. So the informational entropy can also be thought of as the number of bits required to store that information. And this is what's really useful and practical in our digital age, because it also tells us how many bits, if you're sending data, right, over a communication line, and you want to send that data efficiently, if you know that data, this is what leads all the compression algorithms, right, of compressing data across lines, also image compression, data compression. In a sense, you're trying to say, I want to store just the information in that image, not superfluous information. So an image may be, like, let's say an image of maybe a black circle surrounded by white. Well, there's a lot of waste in that image because there's a whole black region and there's a whole white region. So you might ask, what is the information of that image? It really is just the boundaries of that circle, you know, like, and there's the inside and outside are determined by, say, the points of the circle. And I actually haven't verified this, but that's much less than saying every pixel is equally important, right? You can compress that image very well using compression algorithms with fewer bits of information, and then reconstruct that image later from those bits. There has to be an algorithm. And by the way, the information entropy itself does not tell you what that algorithm is. It simply gives you theoretical limits. Like it says, what is the information content of that image? Which would mean, what is the minimum number of bits that would be ideally required to store that image? It can tell you that. But then it's up to you to come up with the algorithm that does that, that figures out how to extract the information from that image and then reconstruct it. And so this is really interesting stuff, right? Just mathematically, engineering-wise, people are very familiar with data compression. The zip file is a compressed file. How that works is that there is redundant. You may have a large file that is wasting space in some sense and doesn't contain a lot of information, and the compression algorithm tries to get at the information, the useful information, not the unuseful information. So this is really fascinating, because right now we're starting to see the connection between information from a mathematical definition related in terms of probability, which is also related to surprise. Because here's the issue. Let's go back to that definition of what is surprise again. Let's just make sure. If an event occurs that's unlikely, you're surprised. So if an event is very likely, like the probability of it is close to 1, you're not surprised if it happens, right? So let's say we have, again, the probability of the sun rising in the east is a good example. The probability of the sun rising in the east is very close to 1, if not exactly 1. It's never 1, because I mean, an asteroid could come along and destroy the Earth or the sun or do something weird, right, to change that at any moment in time, but very small probability. In all likelihood, the sun will rise in the east tomorrow with a probability very nearly 1. So I would be very surprised if tomorrow the sun does not rise in the east. And that's the idea. If the sun weren't to rise in the east tomorrow, I would be surprised. If the sun does rise in the east tomorrow, I won't be surprised. That, if an event has near probability of 1 happening, and that event occurs, you're not surprised. If it doesn't occur, you are surprised because you expected it to occur. So it's really when the event doesn't meet your expectations. You expect something and it doesn't actually happen. So, but that's like, again, it's that definition, minus log base 2 of the probability of the event. So if the probability is 1, the log of 1 is 0, and the surprise is 0, which means it's only ever going to happen, right? There's no other possibility, right, when it's exactly 1. But let's say it's very close to 1. Then you're going to get an informational entropy very close to 0, which you can also call the surprise of that event is very close to 0, which means the outcome of that event is you are likely to not be surprised by. Let's say that's what that represents. And if that event occurs, then it's counter to your expectations, and you will be surprised. So it's interesting to relate all these ideas: surprise, information, 20 questions, and you can see how you can start to see like how everything is related to information then, because and how maybe it's even more fundamental than mass and energy, because like everything you see, right, as the eye is processing images, right, that's information that is going through your eye into your brain, and your brain is storing that information in some way, right? But again, it's probably not it's not exact. It's just storing, some compressed version of that image that you're seeing, so that you can recall that later as a memory, right? And maybe you won't only remember certain parts of it, right? And this could be related to attention, because what you're paying attention to is really what is going to be recorded in some sense. And I may look at the flower, really closely and pay attention to that, and the brain is recording the flower, but not the grass so much around it. I know, I'm aware there's grass around it, but I'm not focusing my attention on that grass, so it's not recording that as much as what I think is important. So it's also showing that interest and attention is where the information comes from, what I'm interested in, which also shows if I limit my attention to one thing, it's limited information. Expanding my awareness to contain more brings in more information. And what do we say? The universe tends to want fewer surprises, more information content, less information entropy, so less unknowns. Because information entropy represents unknown. We said the highest informational entropy occurs for an event that is 50-50, unpredictable. So an event that is completely unpredictable, like a coin toss, has the highest entropy, and the universe doesn't like that. It wants to make it known. It wants to reduce that entropy from 1 to 0, informational entropy. How does it do that? This is like where science comes in, right? This is what we build models of reality, mental models, in order to predict things precisely so that the informational entropy of the universe goes down. The more predictable things are, which we already said, the sun rising in the east, that is something we know. Now that we know it, this is what's really interesting, right? Is how thought and how this is all working is, as we gain knowledge, things become more predictable. and the informational entropy goes down, because we may, let's say we're born as a child, we don't know if the sun's going to rise east, west, north, south, up, down. We have no idea. We learn that at some point in life through our life experience, or somebody teaching us that in a class, that the sun rises in the east. More than likely it's through observation. As a child, you may not know what the east is, right? But you see the sun rising every day in a particular direction, so you expect it to be rising in that direction. So what's interesting is your learning process, it can be predicted by this law of infodynamics, by saying that by you building predictive model, the brain, building predictive models of the universe, it becomes less surprised by what's happening in this world. And the universe doesn't like surprises. We started by saying that. So the brain is, in a sense, a device to reduce surprises by becoming more predictable, by trying to predict nature. Now, what's also interesting is this is also what science tries to do, right? Science tries to explain what's happening in the world. So we can explain science through this informational concept as well, by saying, and we talked about this before, what does science do for us? It goes a little further than just direct observations and says, I want to come up with mathematical laws, usually mathematical laws, that help me explain what I'm seeing in the fewest number of bits of information, right? Because that's the idea. If you can reduce the number of bits required to explain the situation, then and we said it takes 1 bit for every completely uncertain, unpredictable event. Well, and we actually didn't discuss this, but if p was 1, right? The other, so we said if you have a coin, these represent the two extremes. The coin, the fair coin, so 50-50, resulted in an informational entropy of 1. 1 bit of information is required to store that event. Let's say we have a coin that is completely biased, always lands on its heads. So the probability of a head is 1, and the probability of tails is 0. The log of 1 is always 0, which means that the informational entropy is 0. And there is no uncertainty. That means 0 bits are required to store the result. If I have a coin that I always know comes up heads, there's nothing to be gained by me learning the outcome of that experiment. In other words, I don't need to store that event anymore because I know it. I know what's going to happen. And if I can predict it, and I know what's going to happen, I don't need to store the result. I already know the result before it even happens. This is what's interesting, that I'm predicting the future. And if you can predict the future, you don't need to store the result because you knew it. No uncertainty. So in other words, the universe doesn't like uncertainty. Because in one case, H is the typical measure. H was 1 for a totally unpredictable coin toss. And H is 0 for, say, a biased coin that always comes up heads. The universe likes biased coins. It does not like a coin, it does not like the unpredictability of the coin toss. And says, I want to move in a direction to where that is now predictable. I want to learn about that coin. I want to learn about the situation, and this is a mental process, right? But the physical world also obeys this. So this is what's interesting. Our mind obeys the same laws as the physical universe, our brain anyways, in seeking this lowest informational entropy, which would mean the lowest surprise state, which would mean the highest predictability state. If we can predict things better, that is the preferred state of the universe. And you can even think of this as in terms of gravity, because information and infodynamics have been used to describe gravity. Think of what gravity is. What does it cause matter to do? Every particle on the Earth is now together in some predictable way, right? The Earth is a sphere, for the most part. It's not exact. The Earth is like a sphere And because all the particles of mass that were once separate and way out in space, right? And that means unpredictable. Like, just a very informationally, like, I don't know where the position of all those molecules are. I mean, imagine all the molecules that are in the Earth, if they were all just randomly scattered out in the universe, how many bits of information we would need to encode each of their positions at any one point in time. It would be like, it would just be equivalent to the number of molecules times the degrees of freedom, right? I mean, just a massive amount of information to keep track of individual molecules. Whereas when they all come together to form a planet, now I can predict where all those particles are because they're part of the Earth. The Earth moves as a unit through space, right? There's a correlation between the motion of each molecule in the Earth because it's part of this planet, including me. And look at all the particles in the ground. They're not all moving randomly with respect to each other, right? They're all sort of staying still. And that stationarity, or I would say is correlation. They're not still, right? The Earth is moving through the space and the Earth is rotating, but they are correlated. Their motions are, if you know the motion of one particle, you pretty much know the motion of the other particle right next to it, for the most part, right? That's the advantage of gravity, is it brings mass together in such a way that the positions of those individual atoms are now more predictable because the universe doesn't like surprises. Now we can think of this in terms of love too, right? Like, what do we think of even as human beings, right? When two become one, when people become married, right? Or you become friends with somebody, or however, when you form a relationship with somebody, it's because we tend to not want to be separate. We want to be joined. We want to be connected with other people. And you can think of that in terms of information too, because separate people requires more information to describe than when people come together and form a system, just like the Earth, the mass of the Earth comes together to form a planet. People coming together forms a system that has a higher form of order, right? Or a higher form of correlation, predictability. If I know where one married person is, the other married person is probably not far from that person. I see this all the time here at Holden. A lot of people tend to walk with their significant other, right? You often see, you know, boyfriend, girlfriend, husband, wife. I am the exception because I tend to be, you know, by myself a lot out here because I'm the only one that really likes doing this. But the point being that many people prefer to not be alone. They prefer to be with somebody when they're walking or doing some activity, going to church, right? Not by themselves, but with somebody else. And this now can all, in some sense, right, be explained in terms of this law of infodynamics, that coming together, that forming a relationship, leads to lower informational entropy, less surprises, and it's the preferred state. An atom, an electron and proton, right? Why does a hydrogen atom form? Electron and proton separate, shooting through space. I mean, it takes more information to describe an isolated electron moving around and an isolated proton moving around independently of each other than if they come together and form a hydrogen atom. The hydrogen atom has less informational entropy, more order to it, more predictability. If I know the position of the electron, I have some idea where the position of the proton is, right? That's what all those relationships are. That it's now an atom, meaning it's more of a unit than two separate things. And I can predict through quantum mechanics the location of, say, the electron given the location of the proton, the center of the atom. And there's a relationship between the two now. So the universe likes relationships. It does not like things to be apart. It likes things to be together. And that's interesting, because I've often thought, I used to say, love is sort of that property of the universe that brings everything together rather than being separate, right? That tendency. And it could just very well be that love is this drive of the universe to be more predictable. That, you know, and leads to love and compassion and all that, because all of that is about relationships and having relationships, and that those relationships are preferred rather than not preferred. So you see where this is all very interesting. It can also be very intellectual, right? I mean, to someone, you don't need to know math to understand love and to understand compassion, not by any stretch. But if you do know math, and I've often felt, I don't see a disconnect between the physical world and what some may call the spiritual world, although I don't think there is a spiritual world per se. Like, it's all the same world, universe. It's just how you look at it. You know, you can look at it differently. One way, if you look at it through causal relationships, you have what we refer to as the physical world. If you see it as a whole, you may regard that as the spiritual world, just seeing everything together, not as separate pieces. And what does that also mean? As a whole. It's the simplest understanding, which again is totally consistent with this law of infodynamics, in that the simplest explanation for everything is the preferred explanation. And so there's, you know, a lot here, and then also not here. And then in some sense, this idea of emptiness, right, which is, you know, in Buddhism, in so many regards, everywhere, that shunyata, emptiness, that emptiness is form and form is emptiness, can also be an expression of this, in that if you think of the lowest informational entropy state, it's complete emptiness. Nothing. I mean, nothing has to have the lowest informational content, right? And then when we separate the world into pieces, parts, that's when we start identifying them and we define them, right? It's only because I identify the electron and the proton as two different things that need to have their location tracked that I create the need for storing that information. If I don't separate them to begin with, I don't need to store that information. So also just not needing to store information, right? Why do we need to store information? That's another way of looking at things. We tend to, as human beings, as animals, as life, does encode information. I didn't get to this either, but DNA, like people, the genomic structure contains information, and information theory plays a big role in that as well. There's many papers that talk about the information encoded in our DNA, right? You have DNA sequences that lead to all the formations of the organs in the body, and, you know, life itself depends on this information stored in the genome. And then it becomes expressed, right, through the genes and through living, you know, forms proteins, which then forms a living organism from the information encoded in the genetic structure. See, do we think about this? Like, do you see the pattern, the commonality here? And also the compactness. A genetic structure is a very compact, compressed way of storing the information about living things. And what do we say? The universe likes to reduce the number of bits of information. It doesn't like surprises, and it likes to encode into the fewest number of bits of information useful content. And so DNA, at the smallest, look how small it is, right? Center of the nucleus, contains the instructions for your entire organism. I mean, just think about that in that small, tiny little space, right? And the process of extracting information from the DNA is still not completely understood. Just like I said before, compression algorithms, and you can think of the genomic structure as a compressed informational representation of life, and then the process of extracting that information from the DNA is like decompression, right? Extracting the original image from the compressed image is kind of like what the universe does with our DNA. It extracts life from that compressed information about us, from that genetic structure. But this is what the universe does. And why do we seek simple understandings? So why am I even seeking, why do we try to create the equations of physics? I could never finish this expression. The reason we even develop mathematical models of reality is so we can predict reality better. So physics is about predictability. We have experiments that have disparate observations, and we try to come up with a single law. Like, why are we searching for the theory of everything? Why are we searching for the grand unified theory? Why do we develop the theory of gravity? So the theory of gravity, even the way Newton invented it, right, discovered it, just laid it down, right, was a simple mathematical relationship that can explain the force between two objects with certain masses with great precision. And this allowed us to understand the motion of objects, say, under gravity. The reason we can send somebody to the moon right now is because we understand orbital trajectories so accurately, because these laws are fairly well descriptive of what's happening in certain cases. We can predict the outcome of events. So you can think of, like, we couldn't get to the moon if we couldn't predict the motion of objects. And remember, the universe doesn't like surprises, which means the universe likes predictability. The universe likes the ability to predict, to not have surprises. And it would be a surprise if you shot a spaceship to the moon and it just flew out into space. Well, that's not what you want. You want it to fly around the moon and come back home. And these laws condense. You can think of laws, mathematical laws of physics, as a compression process. It's compressing observations into minimal information. The law of motion, Newton's law of gravity, and then of say motion, which is related to that force and acceleration and velocity and all that. Anyone that knows elementary physics knows the basic equations of motion, and under a gravitational field, or motion under an electric field, or whatever. But let's just stick to gravity for the moment. The law of gravity gives you a force. The understanding of acceleration and position and velocity and the derivatives of all these and what that means allows us to predict orbital trajectories of anything, right? Like of rockets. We find that the motion of any objects that have mass, neglecting wind resistance, neglecting all this other stuff, neglecting other forces, right, essentially, obeys that law pretty accurately. We compressed a lot of our observations into a single law, just like the universe compressed all of our biological information into DNA. The human mind likes to create compressed explanations of our experiences. It likes explanations because we can predict things. Now, we can predict fairly accurately the motions of objects with these mathematical laws. That is what the universe likes. It likes that we can predict these things. This is why the brain does this, why we tend to create theories and formulas. So we're even explaining why science exists, right, through this theory of information, in that we like more predictable. I like to state it as, maybe surprise is one way of looking at it, but another way is the universe does not like unpredictability, unpredictable outcomes. It wants to be understood, right? And if you think of it that way, the universe wants to be understood. It wants understanding. It wants there to be less chaos, less disorder, which we could say epitomizes unpredictability, right? When societies are chaotic, or anything's chaotic, right? The random motion of molecules in a gas bumping into each other, you can't really predict with any accuracy the motion of any one particle, any one atom in a gas, because it's bouncing off all these other atoms in a nearly unpredictable, chaotic way. But you can predict the pressure of that gas with fairly large accuracy. Large ensemble, right? A large collection of these unpredictable particles, in some sense, leads to some aspect being predictable, like pressure, energy, right? Thermodynamic variables that come about that are really statistical averages over many, many microstates, leads to sort of predictable macro states. So the world even, is defined in terms of microstates, macrostates, and you can look at information at that level. It depends on the level that you look at, right? Because entropy in physics is actually very similarly defined. We're not going to go into that. It's a whole nother topic. And something I'm also myself learning, the connection between all these various forms of entropy, the thermodynamic entropy as well as this informational entropy, which are two different quantities, but they're very similar even in mathematical form. They are all related in some sense to this number of states. That is how entropy is defined in thermodynamics, as the log of the number of states, accessible states, at some energy level, right? With some macroscopic constraint, like total energy, and it's saying the individual gas molecules can be arranged in many, many different ways and still have that same energy, that same macroscopic energy. And that gives rise to the concept of thermodynamic entropy, very much related. And that's another thing that I'm still working on in some sense, is understanding this relationship between these different entropies. But for the time being, I'm just going back to the fundamentals and really trying to gain an intuitive sense for what this informational entropy is in terms of, things like surprise and probability, and like, what does this mean? And again, my brain is searching for a simpler explanation of things. Can we explain all the different laws in the universe through this single law of information? And that is maybe that's the theory of everything that we're searching for, that still doesn't explain everything. We've gone into this no theory of knowledge. It can't explain the multitude of behavior in particulars, but it may be able to explain, in some level, all of our explanatory theories of nature, right? All of our descriptive, compressed observations could be maybe compressed even further by saying there's an even simpler law to the universe, which is this law of infodynamics, if you want to say it that way, second law, to be precise. And then there is some measurable quantity that we can actually measure called information, and that we can describe the laws of physics, the laws of DNA, the laws of biology, the laws of, everything. Through this understanding of information, it becomes very important. And then what is the foundation of information? Probabilistics. So the fact that the informational entropy is described entirely in terms of probabilities means these probabilities are very important to the fundamental understanding, which we also understand from quantum mechanics being an entirely probabilistic framework, that the essence of the universe is uncertainty and certainty, predictability and unpredictability. And that there is this drive of the universe towards being more predictable. And perhaps, just perhaps, and this is within the realm of knowledge, right, which is not, we don't want to, let's consider maybe the state of enlightenment is understanding everything. Everything is predictable. Everything, in some sense, at some level, nothing is surprising anymore. Right? And maybe that's the ultimate aim of the universe, is the universe wants to become enlightened. The universe wants to reach an enlightened state of total predictability, no chaos, no disorder. Everything's orderly and explainable and perfect order, right? Perfect order. And maybe not in the sense of, and it could just be a matter of perception, right? Because how you define the states, like when we define probability, we have to break it down into events. individual events. But maybe if you don't break it down into individual events, there's a way of looking at the universe so that it is entirely predictable in some grander sense. And this actually leads to even thermodynamics, right? The law of conservation of energy, the law of conservation of mass, in some sense, represents a higher understanding of things, that at some level, we don't need to know the motions of individual molecules to know what the pressure of a gas is. Like, there's a higher understanding, and in a different viewpoint, a different macroscopic perspective, there's a certain constancy, right? These laws of that there is definitely change, but we observe a certain conservation, right? This is interesting because this conservation principle, right? Mass is never created or destroyed. I mean, it's the key of chemistry. Energy never created or destroyed, changes form but maintains the same, is in some sense a representation of a very interesting higher level understanding of nature. And that I may not be able to predict exactly what's happening to individual particles and masses, but I can say something about, I'm pretty confident the energy of that system is going to remain the same. That's a prediction. Or I'm pretty sure that through these chemical reactions, I may not exactly know the outcome of any particular chemical reaction, but I am pretty sure that the mass of the reactants is going to equal the mass of the products. That's the conservation of mass. So, to me, even my own mind is making connections between all these various things, these conservation principles, order, disorder in the universe, information, entropy. I can't, deny the fact that at the moment my brain is sort of playing around, right, with all these different ideas, and it's interesting. Again, not required to enjoy a walk through the woods, to see that holistically, and perhaps to go even beyond these conservation laws, right? Can you see the universe as a whole, an undivided universe? And in that perspective, you obtain absolute certainty, absolute security, absolute predictability, no surprises, right? No surprises. That things may come, things may go. Like, another way of looking at it is, a coin is either heads or tails. I may not know whether that particular coin is going to be heads or tails, but I know it's going to be heads or tails with absolute certainty. One or the other. I know it's going to be heads or tails. And just reframing the question in a different way, you can have absolute certainty. And maybe that's what the brain needs to do, is to reframe the question of life in a different way, to not seek particular answers to particular questions, but to see life from a different perspective where there is absolute certainty and absolute predictability. And that, to go back to our t-shirt example, shit happens and then you die. That is a fairly accurate prediction of life. And we all know we're going to experience painful moments and pleasurable moments in our life. That is, with absolute certainty, I can tell you that is going to happen. And I can also with absolute certainty tell you they won't all be happy moments and they won't all be sad moments. But I can tell you that that is life, the happy and the sad all together. And to see things at that level, there's no longer a need to predict the individual, The need for prediction of an event goes away, and it changes your perspective. And I think that change in perspective is maybe what we're talking about here, that a holistic understanding of the universe, which cannot be represented in words, the immeasurable, right? We measure things, but there is, at some level or in some way, there is an immeasurable quality to the universe, that it doesn't matter what you measure. It doesn't matter what the outcome is. It's an outcome. Whether it's A, B, C, or D, does it really matter? I mean, they're all letters, or 0 or 1. I mean, does it matter? It's all numbers. And just maybe that level of understanding, right? That need to predict. Because another way of looking at simplicity or predictability is don't try to predict anymore. If you're not trying to predict the outcome of event X, you don't need to measure the number of bits required to store that event, and the informational entropy is 0 because you simply don't care. Or you don't care about the outcome. Not that you don't care, but like the outcome, the particular outcome doesn't matter anymore. And if you're not worried about the particular outcome, maybe it shifts things, right? So anyways, I don't want to get too far into speculation. There is some interesting stuff here and some stuff I'm learning, and I guess as I learn it, I'm passing some of that along. Some of this is information, some of it's not information. I mean, going for a walk in the woods and enjoying that, you know, is not something you need to ask questions about or gain information about in that sense, the traditional sense. But just enjoy and love, and you know. Alright, so feels like the end of this morning's walk and discussion, or I guess I'll be walking a little more and then I'll be getting to my work. But it was just kind of a nice little diversion here to have a conversation about things at different levels, you know, at a level of knowledge and at a level of not knowledge. And you know, we're faced with the reality of our life is we must deal with knowledge throughout the day. We have challenges that arise every single day. I mean, I have unique challenges that come up, and how we deal with those challenges is our life. You know, our life is basically that, one challenge after another, and dealing with those challenges, and how we deal with those challenges is our life. So, all right, well, let's end this on a positive note and say it is still a warm, wonderful day here in Ohio. We have had an amazingly long string of warm, wonderful, nice days, which has drawn me outside just like flies to honey. And it's great to start the day this way. So, all right, have a good day. Get outside and enjoy life.